discuss about the criteria for aromaticity. That means actually we should start with what is meant by aromaticity and what are aromatic compounds. So in order to follow the aromaticity, a compound must have uninterrupted cyclic cloud of 5 electrons above and below the plane of the molecule. That means it should have, if it is a 6-membered ring, it should have 6 electrons. Then only the cloud of electrons always rotates in the benzene ring. So this is the criteria for the figure, which is showing that it should have a cyclic cloud of pi electrons in benzene. This is the structure of a benzene. In this totally 1, 2, 3, 4, 5, 6 electrons are there, which are always rotates in a cyclic manner, which forms a cloud. That is the first criteria for aromaticity. So a compound, in order to have a aromaticity, it should satisfy the first rule, that is it should have a cyclic cloud of 5 electrons. That means all the electrons should rotate in direction. Second criteria is the pi cloud must contain an odd number pair of pi electrons. That means already we have discussed in the first point that it should contain a electrons which are oriented always in a cyclic manner. The second condition is that it should contains odd number of pi electrons. That means 1 pair of electrons, 3 pair of electrons and 5 pairs of electrons in this manner. And the third criteria is the most important criteria for an aromaticity is Huckel's rule. A compound should follow Huckel's rule. So what is Huckel's rule? So Huckel's rule means the compound should be, for a planar compounds, it should be a cyclic compound to be aromatic. Its uninterrupted pi cloud must contain 4n plus 2 pi electrons, where n means any whole number. That means it should contains, n means we can take 1, 2, 3, 4, 5, any number we can take. So in place of n, we will substitute those numbers. Most probably it is 1 or 2 is substituted. And for monocyclic hydrocarbons with alternating single and double bonds are called as annulins. And in that case, benzene will comes under annulins. That means it is a hydrocarbon cyclic structure which contains 3 pairs of electrons. That means which is satisfying the Huckel's rule. So according to Huckel's rule and the previous point we have discussed in order to satisfy aromaticity, it should contain odd pair of number of electron pairs. So in case of, by observing these 3 structures, that is cyclobutadiene, benzene and cyclooctatetraene, in benzene only there are odd pair of electrons. In case of cyclobutadiene, it contains 2 pairs of electrons, which is an even number. In case of cyclooctatetraene, it contains 4 pairs of electrons, which is also even number. But in order to satisfy the aromaticity, it should contains the odd number pair of electrons. So in benzene only, benzene contains 3 pairs of electrons, which is an odd number. Hence it satisfies the aromaticity. So hence it is a aromatic compound. By observing these two, by comparing among these 3, benzene is the aromatic compound. Why? Because it also satisfying the Huckel's rule. Huckel's rule means 4n plus 2 pi. So let us see 4 into 1. Let us, if n equal to 1, then 4 into 1 plus 2. That means 4 into 1 plus 2, that means 6, which is satisfying the Huckel's rule. Hence it is a aromatic compound according to Huckel's rule. This is given here. Cyclobutadiene is not aromatic because it has even number of electron pairs, whereas cyclooctatetraene is also not an aromatic compound because it is non-planar and it also contains even number of electron pairs. And let us consider some of the aromatic compounds and whether they are following the aromatic rule or not. So first one is the cyclopropene, which is a ring structure, 3-membered ring structure. So by observing the cyclopropene and cyclopropenyl cation and cyclopropenyl anion, so Neither cyclopropene nor the cyclopropanyl anion is aromatic. Why? Because the electrons are not in case of cyclopropene, even though it contains odd number of electrons, that means one pair of electrons, it does not satisfy the conjugation. That means conjugation means a compound to be aromatic, it should contain alternate double bonds, hence it is not aromatic. Whereas in case of cyclopropanyl anion also, these are not in conjugation, even though it contains one pair of electrons, hence these two are non-aromatic. Whereas by see the cyclopropanyl cation, here it contains almost 1 2 3 resonance structures. Resonance structures means it contains 3 resonating structures. That means in case of cyclopropanyl cation only conjugation is possible. That means pi electrons are rotating in the ring structure, hence it is a aromatic compound according to criteria for aromaticity. And by observing the cycloheptatriene and cyclopentadiene, so in case of cycloheptatriene, it contains 3 number of electron pairs, but these 3 are not in conjugation, that's why it is not aromatic. Whereas in case of cyclopentadiene also, it contains even number of pair of electron pairs, hence it is also not aromatic compound. Just observe these compounds, those are naphthalene, phenanthrene and chrysin. So naphthalene, in case of naphthalene, it is following the criteria for aromaticity. That means it contains electron cloud and which are in conjugation, and it also containing 5 pairs of electrons, which is also following the criteria for aromaticity, and it is also following the Huckel's rule. In the same way phenanthrene and chrysin also, these 3 are following the criteria for aromaticity, hence these compounds are said to be aromatic compounds. Next, coming to the some of the aromatic ions, which are said to be some of the ions which are said to be aromatic. So in case of aromatic ions, the 4n+2 rule applies to the ions as well as neutral species also. Both the cyclopentadienyl anion and cycloheptatrienal cation are aromatic. In the previous point only we have discussed that cyclopentadiene is a not aromatic compound, whereas its ion, that means cyclopentadienyl anion, is a aromatic. And in the same way cycloheptatriene is not an aromatic, even though it contains odd number of pair of electrons, but those are not in conjugation, hence that is not aromatic compound. Whereas cycloheptatrienal cation is a aromatic. Why? Because it is satisfying the 4n+2 Huckel's rule. The key feature of both these, they contain 6 pi electrons in a ring of continuous p orbitals. So that means by observing this structure in both the cyclopentadienyl anion and cycloheptatrienal cation, these electrons are participating the conjugation, that means they contain alternate double bonds, hence these are said to be aromatic ions. And let us discuss the cyclopentadienyl anion. So in case of cyclopentadienyl anion is obtained by the removal of H+ ions from the cyclopentadiene. Here, whereas cyclopentadienyl cation and cyclopentadienyl radical is obtained by the removal of H- ions and H radical. But these two are cyclopentadienyl cation and cyclopentadienyl radical are not aromatic. Why? Because they contain even number of electrons and they are not in conjugation also, hence these two are not aromatic. Whereas look at the cyclopentadienyl anion, it contains 6 pi electrons which are always rotating in a cyclic manner. That means it forms a uninterrupted cloud, which is said to be, hence it is said to be that it is a aromatic compound. Next, coming to the cycloheptatrienal cation. In this also, it is cycloheptatrienal cation is obtained by the removal of H plus ions from the cycloheptatriene. In this also, it contains 3 pairs of electrons, that means 6 pi electrons, which are always participate in cloud formation. That means all the electrons will revert in cyclic manner always. Hence, it is said to be aromatic. But cycloheptatriene is not said to be aromatic. Why? Because these 6 electrons does not participate in orientation, electron cloud formation. Whereas cycloheptatrienal anion is participating in, cycloheptatrienal cation is participating in conjugation, that means electron cloud formation. Hence it is called as a cycloheptatrienal cation is said to be aromatic when compared to the cycloheptatrienal radical and cycloheptatrienal anion. Cycloheptatrienal cation is said to be aromatic, whereas cycloheptatrienal radical and cycloheptatrienal anion are not aromatic. Why? Because they are not satisfying the criteria for aromaticity. That means they are not involving in the formation of pi electron cloud. Hence these two are not said to be aromatic. Only cycloheptatrienal cation is said to be aromatic. Next, let us discuss about the reactions of the benzene. That means especially benzene will participate in electrophilic substitution reactions exclusively. So what is meant by electrophilic substitution? So electrophilic substitution of a benzene is one where an electrophile substitutes the hydrogen atom of benzene. As the aromaticity of benzene is not disturbed in the reaction, these reactions are highly spontaneous in nature. Basic examples for electrophilic substitution reactions of benzene are nitration, sulfonation, halogenation, Friedel-Crafts alkylation and acylation. So what is meant by electrophilic substitution reactions means here an electrophile attacks the hydrogen atom of the benzene. Electrophile means which is a positively charged ion, E plus, which is indicating that electrophile which is a positively charged ion. It attacks the hydrogen atoms of the benzene. By eliminating the H plus ions from the benzene ring, the electrophile are substituted on the benzene ring. And there are some of the examples for the mechanism for electrophilic substitution of benzene. It mainly involves 3 steps. First step is the generation of the electrophile, and second step is the formation of rhenium ion, and third step is the removal of positively charged from the carbocation intermediate. So in the first step, generation of electrophile, so let us take one Lewis acid, and here from bromine, one bromine ion. Here bromine means Br2 means Br plus and Br minus. Hence Br minus is taken by the FeBr3, which is a Lewis acid, and hence it forms FeBr minus 4. Whereas it also generates an electrophile, that means positively charged bromine ion, that is Br plus. And in the second step, this Br plus, that means electrophile. Here instead of writing the Br plus, we are writing here E plus simply. So electrophile, Br plus is a electrophile, hence E plus is taken here. So in this benzene ring, from the benzene ring, one pair of electrons are shifted towards the benzene ring, hence it gets negative charge. Obviously here this will get positive charge, and this will get negative charge. To this negatively charged ions, H plus ions gets attacked. Here benzene ring also contains H, already it contains H. So by shifting these electrons to this carbon atom, this will get negative charge. To this negatively charged benzene ring, this electrophile attack of electrophile will takes place. So in this manner. And in the third step, positively charged electrophile, removal of positive charge from the carbocations. So in the third step, H plus ion from this electrophile is removed, and which is result in the formation of a electrophilic substitution reaction. That means benzene which is substituted with a suitable electrophile. So let us discuss about some of the examples for electrophilic aromatic substitution reactions. That is nitration of benzene. So this is carried out in the presence of nitric acid at 323 to 333 Kelvin temperature in presence of sulfuric acid to form nitrobenzene. This reaction is known as a nitration of benzene. Here also in the same way, here one pair of electrons are shifted onto the benzene ring, then benzene ring will get negative charge, and here already hydrogen is present. To this negatively charged benzene ring, this nitrate ion, that is electrophile, is attacking on this benzene ring, which is results in the formation of a NO2 nitrobenzene. And second example is the sulfonation of benzene. So sulfonation of benzene is the process of heating the benzene with fumic sulfuric acid to produce benzene sulfonic acid. Here also in the same way, these pi electrons which are present in the benzene ring are attacking the sulfurous ion, that is SO3 minus 2 ion, which is resulting in the formation of a carbocation. So with the elimination of H plus ion from this carbocation, you will get benzene sulfonic acid, which is also a electrophilic substitution reaction. And third one is the halogenation of benzene. So when benzene reacts with halogens in the presence of Lewis acids like FeCl3, FeBr3 to form aryl halides, this reaction is called as a halogenation of benzene. Simply here, hydrogen atom of the benzene is replaced by a halogen. Either it may be bromine or chlorine or iodine, whatever may be. Here simply hydrogen atom of the benzene is replaced by the bromide, that means halogens, which is resulting in the formation of a bromobenzene. And the fourth most important example is Friedel-Crafts acylation. Here hydrogen is replaced by acyl group, that means in the presence of catalyst like aluminum chloride AlCl3, here we are taking the acetyl chloride for acylation. That is one of the best reagent for acylation of any compound. Here we are acylating the benzene ring. So in the same way here also this electrophile, that means COCl group is attacked to the benzene ring, attacks to the benzene ring in this way. So the very first step involves the formation of acylium ion, which will later react with benzene. So first acylium ion will forms from the acetyl chloride, that is RC11OCl. It is attacking the aluminum chloride, and which is resulting in the formation of a acylium ion. In the second step involves the attack of acylium ion benzene as a new electrophile form 1 complex. This electrophile, that is acylium ion, will attack the benzene in this manner. In the third step, these AlCl4 returns to remove a proton from benzene ring, which enables the ring to return to aromaticity. In doing so, the original AlCl3 is reconcentrated for use again along with HCl. Most importantly, we have the first part of final product of reaction, which is a ketone. The first part of the product is a complex with aluminum chloride as shown in the figure. The final step involves the addition of water to liberate the final product as the acyl benzene, which is the final step. So this is about the electrophilic substitution reactions of benzene. So benzene mostly participates in electrophilic substitution reactions. So electrophilic substitution reactions means the hydrogen atom of the benzene are replaced by the any electrophile. That means electrophile means positively charged ion which is replaced by the H plus ions of the benzene ring. So some of the examples for electrophilic substitution reactions are nitration of benzene and halogenation of benzene and acylation of Friedel-Crafts acylation of benzene. In these three reactions, hydrogen atom of the benzene is replaced by the corresponding electrophile, which is resulting in the formation of a corresponding compounds. Thank you.